Segment 16. How do we determine the distance, size, mass, and density of the Sun? Now, after going through Kepler's laws and studying Newton, we're in a position to be able to start to actually measure true physical quantities of bodies in space. And we'll start with the closest, most interesting one, the Sun, and then we'll take steps from there. Kepler's laws have scaling constants in them that don't allow us to give the physical parameters of the Sun. Fundamental to everything, if we are going to figure out the physical parameters, is the size of the astronomical unit, the distance from the Earth to the Sun. The equation p squared equals a cubed, Kepler's third law, has an implicit constant of 1. If you take the period in years and you square it, it's equal to the cube of the semi-major axis in astronomical units, and the constant in front of the a is unity. But when you use real physical quantities, then you have Newton's version of Kepler's third law, which is shown here at the top. P squared is equal to 4 pi squared over gm times r cubed. So the constant in this case is 4 pi squared over gm1. And in this case, p is given in seconds and r is given in meters. So which of these quantities do we know? Well, p is the period of the Earth's orbit in seconds, if we're talking about the Earth. Pi is a geometric constant, we know that. G is the gravitational constant, we can measure that in the lab. m1 is the mass of the Sun, which is what we're trying to find out. And r is the radius of the Earth's orbit in meters. It all boils down to determining this. How do we do it? So here are a number of ways that astronomers have gone about determining the astronomical unit. First, you can measure the transits of Venus and Mercury, and by timing these transits when they occur, when Venus crosses in front of the Sun or when Mercury crosses in front of the Sun, as seen from different vantage points on the Earth, you can use these small differences in when the events happen to form a geometric solution to the distance from the Earth to the Sun. Another way to do it is to make an absolute measurement of the velocity of the Earth around the Sun using the Doppler shift. We'll be talking about the Doppler shift later on. This method is not particularly precise. It involves measuring the velocity of stars in the direction the Earth's moving and in the opposite direction and comparing them on average. But since all the stars are moving around, this is somewhat fraught with problems. Another method involves timing the orbits of Jupiter's moons, seeing when they disappear behind Jupiter and when they reappear and when they cross in front of Jupiter. These techniques also can be helpful, but are because of the size of the orbits and the distance are not particularly precise. The best way to do it is to make a direct measurement of the distance to Venus, because if you know the distance from the Earth to Venus, you can scale out, since you know the size of Venus's orbit in a, you can scale out the size of the Earth's orbit in meters as well. This direct measurement is by sending a very strong radar pulse towards Venus and timing how long it takes to come back. So all three of these methods, including that timing method, require you to know the speed of light to very high precision in order to get that distance. But once you've done that, you can get the size of the astronomical unit to a precision of only a few meters. So now we have p, pi, g, and r. So we can take the equation above, Newton's version of Kepler's third law, and do a little algebra, multiplying on both sides by m and dividing on both sides by p squared, and we have m is 4 pi squared over g p squared times r cubed, and this is the mass of the Sun. So now we've derived the mass of the Sun. Once we have the distance, we can also get the size quite easily. The angular size of the Sun is equal to its diameter divided by the distance if you measure the angle in a unit called radians. 1 radian is about 57 degrees. So having measured the distance to the Sun, d, and the angular size of the Sun, which you can go out and just measure with a protractor, you can now get the diameter, d, in meters. So now we know how big the Sun is. With the size and the mass in hand, the mean density of the Sun is easy to calculate. You'll recall from science courses you've taken in the past that density is just mass over volume. So the volume of the Sun is 4/3 pi r cubed, where r is the radius of the Sun, or half the diameter. And the density is just m1 divided by v. So voila, now we know the mean density of the sun as well. So we've determined the distance to the sun, the size of the sun, and its density, all with a single measurement of the distance to Venus using the radar.